Hello, I'm Nigel Griffiths. I work in the Advanced Technology Centre in the UK, part of IBM Europe. In this AX performance movie, we're going to concentrate on nmon and in particular version 12. This comes with a lot of new features to support AIX6 and PowerSix, plus there's a lot of features requested by nmon users. I better confess here that I'm the developer of the nmon tool, and I have been for the past 11 or 12 years. IBM doesn't pay me to do this job, it's a personal project, but they do support me in terms of giving me access to the software and hardware to do the development. This means that there is no warranty given or implied for this nmon tool. It doesn't actually come from IBM, you download it from the wiki website. It is supported by me. We do that via the forum, and you're welcome to send me questions, and we'll do our very best to fix the problems and produce a very quick support for you. But if nmon does mess up, I'm sorry about that, it's my fault, and we'll do the best we can to help you out. So here's the list of 23 most important features that we've added to nmon version 12. The first 14 we're going to look into in detail in the rest of this presentation. From 15 to 23 are some interesting features that we'll say no more about apart from mention them here. Now, nmon isn't perfect. We've had some bugs, so we've fixed those, and you can see a list of all of them actually on the nmon wiki website. For network packet sizes, these are now saved to the nmon file. In the past, we only saved the throughput rates and the number of packets being sent, and you could actually calculate the packet sizes. We do that now in nmon. That just saves other tools and filters that take the nmon data having to do the maths. We produce some warning messages with nmon, particularly network overflow. In the AIX kernel, the counters are 32-bit, and if you have a fast network, for example a 10 gigabit network, then you can overflow these counters quite quickly. In fact, if you're pushing very hard on a 10 gigabit network, you'll actually overflow the counter every 4 or 5 seconds. And there's not much nmon can do if that happens, apart from let you know that this is happening, and this is why some of the stats might be looking rather odd. The same thing happens with the disk stats, where we can have other third-party tools actually resetting the disk stats, and so we go back to 0 and have to start again. In the top process details, when we're online, then we, for large processes, we change the sizes and highlight that they're in kilobytes, megabytes or gigabytes. This was requested by our high performance guys who run some very large processes, and the numbers were getting too large on the screen and all the columns were in the wrong place. It also could help out with Java processes, as they tend to get quite big as well. If you're running nmon for a benchmark or a particular period and you're starting it in a script, the next two might be useful. If when we start up nmon and it's collecting the data about the configuration, particularly the disks, that can be quite a large number of disks, we can now actually kill the nmon process while it's doing that, rather than having to do a kill -9. We can use the SIGUSER1 signal to do that. nmon also returns errors now sensibly if it doesn't like the parameters that you've set, and so you can actually capture in your script that the nmon isn't actually going to collect any data because it doesn't like your parameter settings. With the adapters, we tend to get in the description string not available sometimes. We can look at the nmon FAQ for more details about this. We try and work around it when we hit this problem, but at least we'll carry on going. The not available is actually coming out of the AIX kernel rather than it being generated by nmon itself. The people using EMC disk pointed out that when you're looking at the screen, we have only a certain number of characters for the disk names, and if they're coming out as HDisk power and then a number of digits for which disk it actually is, you can't actually see the digits on the screen, so we rename the HDisk power to just power disks, and then you'll actually find the disk numbers actually on the screen. Also from AIX 5.3 maintenance level 5 onwards, we've had NFS version 4 available, and we now collect stats for this version. Unlike version 2 and 3, where we could show all the stats on one screen, For NFS version 4, all the stats are completely different, so we have a different screen and a different sheet on the nmon file for this actual data. And when you hit the capital N online to look at these, you'll get the version 2 and 3 stats, then you get the version 4 stats, and then it will switch it off. We'll now look at the first 14 improvements with nmon12 in detail in the next few foils. The disk service times have been available in the last couple of releases of AIX, and we've now picked those up in nmon. In the past, people, if you're online, you've clicked D to get the disk graph coming up. You may have found that if you hit a capital D instead, you'll get first of all the same data in numbers coming up on the screen. You hit D again, you'll get the disk sizes and disk free and the adapters and volume group that it's attached to, along with a description of the disk. Now if you hit D again, you'll get the new disk service times. We get in milliseconds the service time and the wait time, and then we get some counts for how many items there are on the service queue or the wait queue, and we get a count for how often the service queue was found full, and we've had to then put things onto the wait queue. Now as soon as we added these things to nmon, we started getting questions, well, what exactly are all these times and counts? Before we go on, I'll highlight the fact that we only save the service time and the wait time actually to the data file. So let's explain what happens when we're doing I/O. The application at the top here calls the AIX kernel via the system call. If there is nothing waiting for the adapter, it will immediately push this to the adapter and it will go into the service queue on the adapter. The adapter will then talk to the disk and ask for the I/O to be started. If we keep pushing things in, then the adapter can take up a certain number of things in its queue, its service queue, but once that limited size is full, it can't take any further requests, and so that's when we increment the service queue full count. At that point, if the AIX kernel is getting more requests for I/O to this adapter and disk, then it'll actually have to save them up into the wait queue inside the AIX kernel, waiting for the adapter to actually have some space available for another thing in its queue. So we have two queues here and two sizes of how large these queues are. We keep this service queue count full when we actually hit the top of the service queue, and from these two things we can calculate how long a request is taking, either service time, that's being serviced by the adapter, or wait time, it's waiting in the AIX kernel for the adapter to take the request. Number 2 out of our 14 items is select a disk. On large machines we have lots of disks, and the records are up in the sort of 5,000 and 6,000 disk sort of area. Some users though don't want to monitor all of them, they just want to monitor the disks that they really care about, perhaps the ones behind the website or the ones behind the database, for example. Previously you could use the user-defined disk groups, where you could name particular disks, put them into a group. But that doesn't work for the service times, because you can't really take a service time across a set of disks. So now we have the -k option. You can name the particular disks that you're interested in. These are the only ones that will be shown on the screen, and you will get the service times. Number 3 is time drift. On large machines, nmon does take a finite time to actually run. And large, I mean either a large number of disks or a large number of processes. This is what takes up the time in nmon. And these times can add up. It means that if we ask for a snapshot once a minute, they will eventually slip down the minute when the actual snapshot takes place, and eventually you can end up with a minute that doesn't actually have an nmon capture in it, because it will straddle the minute boundaries. Now some tools don't handle this very well, and it can get difficult if you're collecting nmon statistics from lots of different logical partitions, and over a day for example, and they all slip at different rates. Then at the end of the day it's difficult to match up all the snapshots are actually happening at the same time. Now in nmon we've got a fairly slick algorithm now, so that we actually calculate how long nmon takes to actually run, and we shorten the pause that we have before we actually start the next snapshot, so we allow for the time that nmon works. And this means that the nmon snapshots do seem to go off very much better at the time that you actually request it, and so at the end of the day the snapshots will still be in sync. Feature number 4 is multiple page sizes that is supported in the latest releases of 5.3 and AIX6. We still have the 4K standard pages that we've had for a long time, but we now have the option of 64K pages. For the high performance guys, they like the even bigger pages of 16 megabytes and 16 gigabytes. But if a program requests data, it will be typically allocated 4K pages, but the kernel will spot the fact that you've asked for lots of them, and it will merge those small 4K pages into 64K pages. By doing this, it's freeing up page table entries that are actually taking up memory inside the machine, and they actually take up CPU when we're searching for them to find a particular page. So by doing this, it's actually freeing up both memory and CPU cycles. When I had a look at this, we have two different sources of data. At the top we have things that are measured in a number of pages, and at the bottom we have things that are rates of how many per second we're doing of things like paging out and paging back in again. Also, looking at this large list, there's 37 of them. I couldn't decide which the important ones and which ones we don't really need to know about. So I decided to actually just capture them all, and then we can make our own minds up about which are the important ones and the ones we want to monitor. If we capture into a file, we'll find multiple sheets in that data file, which will be named, as you can see, mem pages 4K or 64K, etc. Online, if you hit capital M, you'll get this page. If you hit the capital M again, it will convert the top half of this, which is the number of 4K pages and the number of 64K pages, into how much memory that's occupying in megabytes. So that can save you having to do the mental calculations yourself. Many customers are using lots of logical partitions, and some of those are in different time zones. They could be the database for Japan, the database for New York, and the database for London, and they're also having their own local times. This can make merging nmon files together quite difficult, because you have to remember how many hours difference there are between each of the captures and offset that. So instead you can use the -G to use Universal Standard Time, or as we here in London, UK, like to think is Greenwich Mean Time, and as I live 5 miles from Greenwich, I like to think that it is actual fact that the British invented time in the first place. Another option is that customers are using nmon to capture lots and lots of snapshots. The timestamps, as you can see, have 4 digits, so we can go up to 10,000 snapshots. If you go over that, it actually gets difficult to sort the file and get them in the right order. Now, my first response to this was that you're all completely mad if you're trying to do this, 10,000 snapshots in one particular file. But the nmon user said no, they really want to do this, and using the old rule that the customers write even when they're completely bonkers, we added a feature here, the -W, and you can put in a number of digits that you want your snapshot numbers to be. And there's another extra line for the AAA, says timestamp size, so that your tools can pick out how many digits these will actually be if you're post-processing your nmon files. In my humble opinion, 4 digits is more than enough, but you now have that option to capture thousands or millions of snapshots in a single file. In fact, if you go to the full 16 digits, I'll be dead for about 1 billion years by the time you get to that, so I won't probably worry about the problem from then on. Number 6 is, again, by popular demand. There's some extra data out of the libperstat library that has all sorts of numbers in there, and we tend to, in the past for nmon, pick out the numbers that are actually useful for help you tuning and monitoring your machine to understand what's going on. But I kept getting requests for, could I have this column, could I have that extra column, and in the end I decided, look, we'll just dump all the numbers out of these two data structures, and I called them raw CPU and raw LPAR data, and then you can deal with those numbers as you like. You have to be careful, some of those numbers are very big, but it's not my problem. You've got the numbers, you can do what you like with them. Number 7 is high priority nmon. On some machines, particularly if you're running batch and you're running at near 100% busy all the time, it can be difficult for nmon to actually get scheduled and back on the processor when it actually wants to do a snapshot. And so we have the -z option, and we can put in a nice value. If you go for -20, then nmon gets a boost in its priority, and it will probably get in ahead of your other processes. This can be good because then nmon's captures don't get postponed and we don't have time lag problems. But of course then you might have to decide whether nmon is the most important thing on your box or not. We didn't fix nmon in memory. We could have pinned it in memory. Particularly nmon can get large. You've got a large number of disks or a large number of processes, and if you've got an actually limited amount of memory, nmon could actually be taking up quite a large piece of your memory space. It will grow up to 1/4 of a gigabyte. It can't go beyond that by the way it's compiled, so there is a sanity check in there. Number 8 is the Virtual I/O Server Shared Ethernet Adapter Stats. Many people are using nmon to capture what's going on the Virtual I/O Server, or VIOS, and it's important that we monitor what is happening over the Shared Ethernet Adapter. That's one of the 2 prime functions of a Virtual I/O Server. A lot of people don't understand that when you look at the network stats on the VIO server, they are the packets that are coming in and out of the Virtual I/O server itself as a copy of AIX. What's being passed over the C, the Shared Ethernet Adapter, is actually happening at level 2. It's a bridge and it doesn't really enter AIX as such, and so the numbers aren't recorded by the standard AIX tools. This is why we have to use the entstat command to actually get this data. We switch this on with either the -O to put it into the file, or we hit O when we're looking at it online. And I thought C and Ocean, O, is about as close as I could get for something that was obvious. The S key is already used for other reasons. nmon is actually running this command internally and capturing the data out of it, so there is a larger overhead. Normally we use the API to get the data quickly and much more efficiently, but the importance of the data means that we do actually want to capture that directly with nmon and save it to the file or show it on the screen. Feature number 9 is partition mobility, and for this we do require a Power 6 machine. Partition mobility is where we take a complete logical partition running on one machine with its users and applications all running, and we jump it to another machine without interrupting its service. Fortunately, nmon just looks like another process running on this logical partition, and it just migrates or jumps with everything else, so it doesn't really affect nmon. But then we thought again, and we need to be able to capture when these things actually happened for performance reasons. We actually do that with this dynamic reconfiguration API. And I won't go into the details here, but you have to make a special system call and you look at the dr.h file, and then you can actually ask for signals to be sent to your process, in this case nmon, as we actually do this transition between the 2 machines. We actually get it a number of times. We get a check signal to say, are you okay about this? Then you get a pre-signal that says we're just about to do that. Perhaps the application wants to change the way it's operating while it actually happens. Then it actually moves to the new machine, and then we get a post signal saying it's all over now, it's completed, you can go back to your normal operation or do your processing in a different way. Now these events are not synchronized with the normal nmon outputting data to the file, or for the screen for that matter. This actually makes it difficult to actually include in our regular snapshot data. So instead we put the data into the BBBR section for dynamic relocation, and that way we can actually capture when the logical partition jumped between 2 machines. In fact, by adding this feature we actually now get more details about whenever dynamic changes happen. The same protocol is used for when we add a CPU or take 2 CPUs away or add a couple of gigabytes of memory. So these are all monitored and saved in the file as well. So what actually changes when we actually do partition mobility? Well, clearly it's between two machines, so the serial number will be different. The logical partition number and name may change. There's already a logical partition with those same details on the target. The logical partition will be the same in terms of the number of CPUs and its setup and the amount of memory it's got. But we might actually be running now on a machine with faster CPUs or slower. We may actually be in a pool of resources which is larger. This may actually create a jump in our performance stats, either for good or for bad, as we jump into a different pool of resources. But now, because we're capturing this data, we can actually explain why that particular jump in the graph actually happened. Online, at the bottom of the logical partition screen, we get these events, check, pre and post, and what's actually happening, and we actually save the serial numbers before and after, so you can actually see when that happened. Into the output file, as I said, we have the BBBR section, and in the example below we can see a check, pre and post. The CPU number is 2, so that's what's actually changing, and we can see the word add here. This is the operation that's being performed. Similar things happen when we actually do partition mobility. Now feature 10 covers something that comes in with AIX6. This is workload partitions, or WPARs. We can use nmon inside a WPAR, but a view of what it can see is actually quite limited. It can only see its own processes and its own performance data. Also note that inside a WPAR there is no disks or adapters or paging space. These are features of the global copy of AIX, not a WPAR. So there's little point in monitoring a WPAR by itself, unless of course you're the systems administrator of a particular WPAR and you haven't got access to the global level. At the global level, of course, you can see all the workload partitions running in this copy of AIX. When you switch on a WPAR, you start it up, then it creates a workload manager class dynamically as it does that. And we can monitor these things either as WPARs and the statistics available there, or we can use the workload manager classes and see some of the data there as well. We can switch on both of these features to get actually more information, or if you look at top processes and then hit the capital U, you get the user command, and that will include the WPAR name, so you can see which command, which process is running in which WPAR. On the next screen we'll actually see a worked example of this. It's probably more interesting. At the top then we have the workload partition information. We see the name, then we have sys or app for system or application WPARs. Defined means it's not actually running, but active tells us that it is running at the moment. Then we see the physical CPU use of our workload partition. We only get user and system time because you don't idle or wait actually inside a WPAR. That runs at the sort of global level. We can see some information about the memory. We can see the in-use memory of a particular workload partition, and the num_perm value tells us how much file system cache is being used by this particular WPAR. Then there's some other classic useful information like the run queue, the process switches, and the forks happening inside the WPAR. If we look at the workload manager details, again we get some more information here. The workload manager way of sharing out resources and managing it works for our WPARs as well. In this case though, we're using the default shares for everything, so it's not that interesting an example. At the bottom we have the top processes, and we can see this extra column in here, the WLM class, to tell us that this, in this case our workload partition WP03 is running some programs here, and the things in the system class are running in the global copy of AIX. With our workload partitions we have application mobility, where we can move a WPAR from one copy of AIX to another copy of AIX, either in the same machine or a different machine. And again, because we do the dynamic reconfiguration API, we get the same information sort of captured as we do these sorts of operation, but in this case the serial number may not change because you could be jumping between two copies of AIX running on the same machine. Again, though, that the environment could be different. We could be jumping from a copy of AIX with 2 CPUs to a copy of AIX running 8 CPUs, and we will see a dislocation in the CPU statistics as we move from one copy of AIX to the other. Here's examples then of the before and after doing application mobility. We can see the check and pre-phases going on in the bottom of the WPAR panel. We can see here that we've jumped between two different logical partitions, but the serial number is the same, so it was on the same machine. Feature 11 lets us capture data about dedicated donating logical partitions. This is related to the Power 6 based machines. What we have here is that with a logical partition with dedicated CPUs, we can set a flag that says when our logical partition is not actively using all these CPUs, they can be temporarily loaned to the shared pool and used there. We see here a capture from the HMC when we're configuring up our logical partition. You can see dedicated has been selected, and at the bottom we see this field that says processor sharing allow when partition is active. Not terribly obvious that is these dedicated donating logical partition, but now you know, and you can find this flag to set it if you want to go dedicated donating. And it does make sense, otherwise you can waste CPU power in your dedicated logical partition just because you can't share it to somebody that is desperate to get CPU cycles. If we hit P for the partition information at the bottom, we have this extra data. When the logical partition is idle, then in actual fact all of the CPU cycles are donated to the shared pool. And then when this logical partition starts using its CPUs, then it will immediately bring back the CPU cycles for its use. And also note that it will always bring back the same CPUs. It has sort of ownership of the CPUs that you don't get with regular shared CPU logical partitions. So this is quite a good learning exercise. I was expecting it to donate them if a logical partition was demanding CPU cycles, but in actual fact they're all donated and we pull them back when we actually need them. Now we actually captured this data and ran through a peak in the workload to monitor this bringing back of the CPU power into the dedicated donating logical partition. And we can see here that as we go through our peak that we generated via our fake workloads, we can see that the hypervisor is bringing back sort of proactively more CPU time than you actually need to run our logical partition, and releasing the CPUs slowly as we get over this peak. It means that this dedicated donating logical partition always has the CPU cycles if it needs them, but if it doesn't, then they are freed up and put into the shared pool. Exactly what we want for performance reasons. Another feature that came in with AIX a couple of years ago, and we noticed a couple of years ago, is this folding away of a CPU. AIX will realize that if you've got a lot of virtual processors, so that it can spread out and use lots of different CPUs in the machine, that's not actually very efficient if you don't need your CPU cycles. You don't want to start on all 8 of these CPUs if you've got very little to do apart from running a timer interrupt or something. So it will temporarily switch off the virtual CPUs. It doesn't actually do anything, it just doesn't schedule work onto those particular CPUs, so it never has to jump to them and run. Now there is no statistics for the folding of the CPUs. This is an actual internal thing to AIX, although we've seen it in practice by carefully monitoring with nmon what the CPUs are actually up to. But we put in some heuristic checks and we can detect when AIX stops scheduling work to a particular CPU, and so we started counting how many CPUs are folded away. And again we ran a similar workload going through a hump in work, and we can see here again AIX is unfolding and folding the CPUs away as need be and spreading out onto more CPUs if that gives it a performance boost, and switching them off if it doesn't give it any performance benefit, and it can let another logical partition have more time on the CPUs that it's not using. Feature 13 is the multiple shared pools. Again, this comes in with the Power 6 based machines. With Power 6 we're using the HMC7, and I've shown some panels here of how you set this up. On the HMC you select the list of servers, then you select a particular server, then configuration, and the bottom item is the shared processor pool management. Again, this can be quite difficult to find if you're looking for the first time. At the bottom then we see these two panels that you bring up. First of all, the pools, and you have a list of the pools and how many CPUs are assigned to them. Any unassigned CPUs are in the default pool. We can click on the shared pool name and you actually give it a better name, and here we see shared pool 1 has been allocated 1 CPU. If we click on the partitions tab, then we get a list of all the partitions, and it then tells us which logical partition is in which pool, and we can click on the name of the logical partition here to change which pool it's actually in. In this case, the bottom two logical partitions are in shared pool 1 and the rest are in the default pool. So why do we want multiple shared pools? Well, there's two reasons. One is, the most important, is for licensing reasons. So if we've got some software that we perhaps licensed for a number of CPUs, let's say 8 as an example on a 32-way machine, then all the logical partitions that are using that particular application or middleware, they can all be assigned to a particular pool, and then we can guarantee collectively they can't go over the number of CPUs in that pool, if that's the way we set it up. This means that we can guarantee that we're legal and above board with our licenses, but at any one time the license, the CPUs, can actually be moved between those logical partitions on demand and as needed at any one particular point in time. There's another reason for using multiple shared pools, and again this is for performance control. If we want to make sure that some logical partitions get more resources than others. nmon, the shared pool number, has been added to the LPAR numbers in the file, and we have a new sheet of information called pools, and that gives us the details that we can find out about the pools. The logical partition saving this data can only find out about its pool and the global pool. It can't find out information about other shared processor pools. If we look in online, we can see it like this. At the top right we can see the one there is shared pool 1, that's our pool. And at the bottom we've added some more information, and on the left we have A, which is a summary of how many CPUs are actually in the available in the shared pools altogether. At place B there we have how many CPUs are in my pool and how many CPUs have been allocated in entitlement to logical partitions in my pool. So we can see that we have 1.5 CPUs allocated. There's an extra half a CPU that could be set as an entitlement. At the middle right we can see what's happening in our actual pool. We have 2 CPUs in the pool, and we're currently using only 0.26 worth of CPU time among all the logical partitions in that pool. And at the bottom right we have an overall use of all the shared CPUs. In this case we can see we're just using 0.27 of a CPU. The bulk of that is in my pool, and there's 0.01 of a CPU being used in some other pool. And finally we get to the last one that we're going to look at, fiber channel stats. And these are not available as a programmer, as an API, and a little bit like the cstats, we have to use the fcstat command to actually get this data. So there is a performance hit actually rerunning this command to get the data. Now if we're collecting once a minute, I don't think we'll notice, but if we're doing it second by second, then there will be a performance hit as we run this command to find out the information. Also, you need to note that this is a point in time. This is as the fiber channel stat command wants to report this information. It's not really the average over the period. You have to look at the fcstat command for more information. Now we hit the caret sign, the little up arrow sort of symbol on your keyboard to switch this on, or we use the same thing for switching it on to collect it into a file. And a little bit like network, of course this is a storage area network, a little bit like an Ethernet network, we're going to collect the receive and transmit kilobytes per second and the number of requests in and out. And from that we can actually calculate the size, and as we can see in this example, there's a 4K buffers are being written out. If we save this information to the file, then we're going to have FC read and write, and the FC transfers in and transfers out. Now, one extra bonus, if you like, with collecting this information is that if you have fiber channel tape drives connected to your SAN, then we're going to actually find out what your tape drives are actually up to. And from talking to the administrators that have fiber channel tape drives, they tend to connect the tape drives to a particular set of dedicated fiber channel adapters, and then their disks on a different set of adapters. They don't mix the traffic to these two different sorts of device. And so we can actually see what the tape drives are actually running. And this is something that we've been looking for a long time in performance monitoring, actually finding out what our backup or recovery rates are from our fiber channel tape drives. A few final words then on nmon. I do encourage you to take the latest stable version of nmon. Changing one file, you can hardly call it an upgrade. You can very easily go back. Do not run old versions. I find a lot of customers running years out of date versions with known bugs in them that we fixed 4 or 5 years ago, and they're worried about the numbers, and it's your own fault. Number 2 is for uncapped shared CPU logical partitions. The utilization numbers are fundamentally unsafe. They are not going to tell you how much CPU time your logical partition is using. This is because as you get up to your entitlement, the utilization number gets to something like 95%, and then as you go over your entitlement, you can go up to 10 times more CPU time than your entitlement, and the utilization number will change from, say, 95 up to 100%, and you've really no idea how much physical CPU time you're using. So I recommend that we now start thinking in our big machines using shared CPUs that we monitor physical CPU use. nmon's particularly good at that. If you're using the AIRX commands, you're looking for this physical consumed or PhysC number. nmon is fully supported by me and the other nmon users and developers. You'll find this on the Performance Tools forum. You'll find the website on the next foil. I encourage you to have a look at the nmon FAQ if you've got a question. Look at the manual page. We will update that shortly. And then look at the Performance forum to see if there's already a question and answer there. If not, add a question to the forum. And I check the forum most days or every other day, and hope to respond to you quickly. I'll leave you then with these web pages for nmon, the analyzer, Excel analyzer. We also have a new tool called the nmon consolidator that will take many nmon files together and give you a consolidated view. Very good for server consolidation, taking lots of machines and bringing them to one, what would actually happen, or for looking at all logical partitions on one particular machine. At the bottom there's the place that you can click on to get to the Performance Tools forum.